always like to kind of start the class with kind of an idea of science, because I get frustrated when I listen to public media do reports on how totally unaware of how science works most people are. So I always like to kind of come back and say, okay, how does science really work? And how then, as we as a society, can come up with some understanding that we do a job that assures that we have the best answer at any point in time. Okay? But the reality is we learn and we create more technology. So the more we learn and the more technology we create, the better our answers are going to be. So yes, science has to go back and say, oh, we need to change this answer because we learn new things. So to put that in perspective, I was born the year that Watson and Crick wrote their paper on DNA, on how they thought DNA was constructed and how they thought DNA worked to code information for cells. So in my lifetime, we've gone from, hey, this is the way DNA works, and this is the way it looks, to completely sequencing the genome, so that we know all the genes in the human body. Just yesterday, or over the weekend, there was a published paper released in Nature where scientists have taken the genes from breast cancer cells and done a complete analysis on just the cells that are in breast cancer tumors. That allowed them to take breast cancer and divide it into 4 brand new categories of breast cancer. And it turns out that one of them, the genes are all almost identical to the cancer cells in ovarian cancer, which means we've been using the wrong chemotherapy. And so now we can tie the genetic information in the tumor cell to a type of chemotherapy that works better. So if people have this one particular type of breast cancer, they would have a greater survivalship if we used the same chemotherapy as we were using for ovarian cancer. So that's the way science works. We learn things, we extrapolate from it, and we try to make decisions from it. So the whole purpose is to assure at the end that we have credible information that we're dealing with. All right. So if you look back in history, science was a hodgepodge of people playing around with no coherent pattern to which it was done. So nobody could repeat experiments to get the same data because everybody was kind of doing their own thing. So it was in the 1500s when Bacon and Descartes actually thought, wow, we need to change what's going on in the 1600s. So what they did is they created this process called the scientific thought process on how you develop an experiment, how you run an experiment, and how you draw conclusions from that data. And then they also created what were called the Academies of Science. So the first 2 were in England and France, and we have the American Academy of Science in the United States that is involved in this process. So the end product out of this is that we want science to produce reliable, objective, and testable information. Okay. So there's kind of 2 processes involved in it. And there's kind of 2 ways of reasoning. There's inductive reasoning and there's deductive reasoning. And we kind of have to use both. So an inductive method is where the process involves numerous experimental observations. So if you did one experiment and you got one set of data and you published it, how do we know your data is credible? Well, we know it's credible because we repeat experiments repeatedly. And if we get the same results all the time, then we know we have some more credible data. So it's really kind of important that we do that. So the whole idea of this inductive method is to create what we call truth in science. And actually, truth in science is tentative. And at any point, it's proof beyond a reasonable doubt. But what you have to remember is that's at any point. Would you go to a physician who graduated in 1950 and has never upgraded their education? Who's still doing the same things he was taught in 1950? Would you be comfortable with that? No, because most of the technology we use today didn't exist. No CAT scans, no MRIs, none of the stuff we use today exists. So that's why most people in medical professions have to do continuing education, because things change. If I taught you what I learned in college, you guys would think I was crazy, because what I've learned has been modified appreciably since then, in terms of a lot of the physiology. Anatomy hasn't changed, but physiology is. So what we want to improve is reliable observations that have been made, that we have repeatedly tested the data to assure it wasn't a random event that can't be repeated. And when we begin to draw conclusions, we have to understand what would make the data false. You know, in other words, it's not falsifiable by other credible observations. So we have to understand what would make our data false. All right, so the basic premise is we start with a hypothesis. And a hypothesis is an educated speculation or question about how a process works. And that guides the research that you do, because you're trying to answer that question. Right? So there's actually a lot of concern right now that a lot of the funding for science is no longer public funding for public good, but it's driven by industry that wants specific answers. And they want answers in a specific way, which can jeopardize this whole process. So a good hypothesis is consistent with what is already known. It's testable through experimentation and observation. And that's what defines science. Is it has to be something that you can develop an experiment for and test. If it's not testable, then really science can't answer that question. Okay. And then it has to be falsifiable with other credible evidence and observations. So it's kind of an if-then. So if the original observations are correct, then we kind of try to gain where our end result should be, or we should be able to kind of have an estimate of what the outcome should be. Okay. Some of the coolest science has been done with some amazing, really simple stuff. Like Watson Crick got their Nobel Prize for blue toothpaste to create a model. Okay. So the problem with deductive reasoning is you can get in trouble with it quickly. So when you think about deductive reasoning and logic, the thing that is critically important is that you have to have a premise, and then you have to have a conclusion, and there has to be some connection between the premise and the conclusion that makes sense. So if you consider the argument, all men are mortal, so that's the premise. And Socrates was a man, so therefore Socrates is mortal. We already know that because he's dead. Right. So what if you went to the restaurant and the local football team was in there, college football team, and you noticed that the only football player that ordered a steak was the quarterback? So your premise would be only quarterbacks eat steak. Because your observations told you he was the only one that ordered steak. So then you go to another restaurant and there's a guy, John, eating steak. So therefore you conclude John is a quarterback. That would get you in trouble, wouldn't it? Yeah. So that's what we try to avoid in science, right? So the whole key to a hypothesis, where you're using a premise and developing experiments to get a conclusion, is that the premise and the conclusions are both correct in the end product. Right, so The other thing, because you're going into some form of allied health or physical exercise physiology or some type of career where data determines what you do. And you usually have to read journals to stay up with current stuff. And journals are all done with statistics. So if you don't understand statistics, then you can never figure out whether what you're reading is crap or not. And there's the dilemma. Because people print crap. Just go to the web. This one's a great one. Go to the web and put in Flat Earth Society. And you'll find a group of people who still believe the Earth is flat. And that the round pictures there were all concocted by Hollywood. Look at me like I'm crazy. All right. So anytime you look at an experiment, one of the things you have to look at is sample size. So if you're looking at data and they tell you that 1,000 patients were involved in this experiment, and then another set of data tells you 5 patients were involved in the experiment, which one would you be more likely to believe? The greater the number. So sample size is critical to making sure that random variations have been weeded out. Because you and I are all genetically unique. So we need to make sure we have that broad random size of genetic uniqueness to make sure, particularly if we're dealing with drugs in human populations. And it's so critical that even with drugs, if you've only tested women, then you can't market the drug to men. If you've only tested men, you can't market the drug to women. So when the human papilloma virus came out in terms of the vaccine, yeah, they'd only tested women. So all the ads targeted women, and everybody got mad. Just, well, wait a minute, they get it from guys, so why aren't guys getting this vaccine? They didn't test it on guys. So now they've had to go back and do another set of experiments. So they can actually market it to guys too. Yeah. So that's actually what sample size is all about. What's your sample made of, and are you sure about the end products of that? So anytime we do an experiment, we have to have one group that we're judging against the other group. So we have a control group, and we have an experimental group. The sample size should be very similar. The makeup of both should be similar. So you can't have guys in a control group and gals in an experimental group. You'd have to have a random assortment of both. Okay? And then the control group is not given the experimental variable, and the experimental group is. So the way we do drug research is that we have a control group and an experimental group. The control group is given a placebo. They aren't given the drug that's being tested. And then the experimental group is given the drug that's being tested. And then that allows you to look at, for example, if it's a new cancer drug, you can look at mortality between the two groups. Did actually more people survive this cancer when they had the drug versus not having it? And you actually sign up for an experiment like this, and you don't know whether you are in the control group or whether you're in the experiment. You don't know if you're getting the drug. And we have to do that to absolutely make sure that we have a way of comparing the data from the drug with people who didn't get the drug. Of course, the inverse could be true. There could be a higher mortality over here with the experimental group because the drug created problems we didn't from the patient. So it's really interesting to look at. So you want identical treatments except for the variable being tested. That would be the drug. All right. And then an independent variable is typically the variable being manipulated by experiment. And the dependent variable is the one that is not being manipulated. Okay. So when we do drugs, we actually use the placebo because there are psychosomatic effects. And then no matter how you think you're not biased, you're biased. There's no way it's not biased. And you can try all you want not to be biased, but you're still going to be biased. So usually when we do drug experiments like that, we do what are called double-blind studies. That means that none of the patients involved in the study with the control group or the experimental group know that they're on the drug. They all think they're on the drug. And none of the practitioners collecting the data know who's on the drug. And it isn't until the experiment is over and you begin to analyze the data that that information is brought out. That way there can't be a bias to what's going on. So double-blind studies are critical to making sure that bias is influenced. Then what we use is mathematics to try to ascertain whether the end result we got could have occurred simply by random probability, or whether the end result we got is most likely not just random probability. So we use statistics to do that. We look at the difference between the control and the test subjects, and making sure that random variability is not what's causing the effects we're seeing. And then the other thing that's critically important is that when you publish in a journal, other scientists get to review your work before it's ever published. That way you have somebody else looking at what you did to see if you have any blatant errors in thought or logic in it, or statistics or other things. So this critical evaluation by peer reviews is really, really important. What it does is ensure that what we are left with as a public is honesty in terms of the information coming out that's been objective, and it is good science. And then we're all happy. All right, so this is the one I love, where you watch a public TV show, and there's these guys arguing, and one guy says, well, this is fact, and the other guy says, oh, no, it's not fact. And I'm just like laughing. Because fact is all an interpretation of data. All right? So in science, if we say it's a fact, we're trying to say that it's information that's been independently observed and verified. In other words, it's just not my thought. Other people have come to the same conclusion. And then the most important thing to remember is what I showed you first. Proof in science is tentative. Because the more we know, the more we can refine what we think is a fact, right? So I always like to give my colleagues in physical science a little rub, because chemists have laws, physicists have laws. You probably learned the laws of thermodynamics, right? Well, those have been tested for centuries, and we're pretty darn sure they seem to work all the same way. So anytime something's been tested to that extent, it becomes a law. There are no laws in biology, because it's much more complicated because of genetic variability. So we have theories. And then I just love it when you hear somebody on the media say, oh, it's just a theory, so it's not true. Well, wait a minute. A theory is an understanding based upon a summary of conclusions drawn from observations. It's actually not merely a guess or a conjecture, but it's actually an explanation that we can use to make predictions. Now, does that say that a theory can't change? No. If we learn new stuff, then in science we would have to do change what we believe. And that's the beauty of science, is we don't pigeonhole ourselves into a belief that can't be changed. Because if we have credible data that suggests we weren't quite right, then we need to change what we thought, right? That's why you can't use a textbook made in 1950 today. All right. So you're taking anatomy and physiology. If you went to Washington State, you take anatomy first and you take physiology second. I've never liked that because you can't integrate thought. So I like teaching anatomy and physiology together. And I have taught the other way. I teach anatomy, and then when I taught physiology, I'd have to reteach anatomy because everybody forgot. So it's like, okay, let's put them together. So anatomy is actually just your physical entity, right? It's the science of structure. It's relationships between structures. And the reason why we do dissections is because we can learn the three-dimensional relationships through dissecting. And we can use some real cool imaging techniques to come up with some really cool information. Probably one of the coolest ones in recent times is work being done by some neurologists at University of Oregon Health Sciences, and they're working with stroke patients. And so because they can look at what's absent after the stroke, the paralysis or the loss of some cognitive capacity, then they can actually image where the brain was damaged. Then they know what area of the brain was damaged and correlate that with the absence or what the patient lost in terms of the stroke. Well, now what they've been doing through OT and PT with these patients and retraining them to do tasks that they lost because of their stroke is they're imaging the brain, and they're using infrared that shows where the brain is the most active while they're doing certain tasks. And they've been able to map how the brain retrains itself and what areas of the brain can actually be retrained to do certain tasks. So isn't that cool? So physiology is how the body works. All right? So there's a gamma physiology. And so at a starting point, you have to decide kind of, well, what level of physiology are you going to teach? And then if you get into a program, you'll take a pathway phys class, which deals with all of the abnormal stuff, right? So what we're going to do is we're going to do normal adult physiology. And it would be different if you were dealing with newborn babies. It would be different if you were dealing with people in their 80s. That's why in medicine we have specialists that deal with newborn babies. And we have doctors that are specialists at dealing with aging people because the physiology changes. So if you don't believe that, take the pulse of a newborn baby, take the pulse of a 30-year-old person, and then make the pulse of an 88. Would all those pulses be the same? No. Yeah. Because our physiology changes. Right. So we are going to start with adult physiology. And we're going to do both male and female and talk about differences between the two where appropriate. Okay. But what you have to remember is genetic variations in human being. I don't see anybody in here that looks the same. So does that mean you and I would always have the same side effects from a drug? No. That's the difficult part in managing is all those genetic variations. Okay. So when we look at anatomy, there's various levels at which we can do anatomy. We can do surface anatomy. That's what we were doing yesterday. It was learning names to the surface of the body. And we're looking at surface anatomy. Gross anatomy is anatomy that you can see with your naked eye. So, for example, when you dissect cadavers, it's called gross anatomy. If you're looking at structures, you can see with your naked eye. There are a couple ways we can teach anatomy. So in this class, we're doing systems anatomy, where we're going to start with the integumentary system, this unit eventually, and then we're going to do bones, and we're going to do muscles, and we're going to do the nervous system in this unit, this class, this quarter. And then in the winter, we're going to continue that and do the rest of the systems of the body. By doing that, we can kind of integrate ideas across systems, but really focus on a single system. But clinically, you don't do that. So clinically, you go in because you got a shoulder that hurts. So when I teach the clinical anatomy for the PTA or OTA programs, I totally change the class into regional anatomy. we do head and neck, and all the systems in the head and neck. We do thorax, and all the systems in the thorax. And then we do the arms and legs, all the systems in the arms and legs. And that moves somebody into thinking clinically. So that's why most programs, even though you have taken this beginning class, are going to have some unique classes that you have to take that move you toward that clinical thought process. Pathophysiology, a classic example. And then, anybody interested in the X-ray text program on the other campus? And you would become specialists at radiographic. Those cool images. People who are involved in looking at how babies develop over 9 months inside mom are developmental anatomists. And the early part of that, where you develop your organ systems, would be embryology. So it would be embryologists are specialists in the first 2 months of development, when you develop all your organ systems. All right. Cytologists, they just like cells. They don't really care about a bunch of cells. And pathologic anatomists are the ones that use microscopes to look at slides to determine whether you have normal cells or abnormal cells. Pathologists. Physiology can be subdivided appreciably. And what we see with the subdivisions in physiology is it mirrors the subdivisions that we see in medicine. Because you can be a generalist, but it's really hard to be a specialist at everything. Okay, so we have to have specialists, and we have to have generalists. So we have cell physiologists. They play around with cells. We have systems physiologists, people that are specialized in systems. So when we think about systems physiologists, you have neurophysiologists because they're specialists with the nervous system. You have endocrinologists or endocrinology because they're specialists with cells that make hormones and understanding hormones. You have cardiovascular physiologists, cardiologists, that are specialists at the heart. You have immunophysiologists or immunologists, which are specialists at the immune system of the body. You have respiratory physiologists, so RTs, respiratory therapists. And you have renal physiologists and reproductive physiologists. So, what would be the doctor that's a reproductive physiologist? So what about renal physiology? It's the kidney. So yeah, the funny part about this one is you go to a urologist if you can't pee. So a urologist is a specialist at the tubes and the bladder and the urethra. But if you're not making pee, then you go to a nephrologist. Yeah. So with renal physiology, we have people that are physiologists on how urine is made, nephrologists, and then people that are specialists on helping to pee, urologists. Okay. So lots of specialties out there. Oh, then pathophys would be pathologists that are looking at physiological processes. Exercise phys, and it's kind of a cool one, brand new program the last 10 years downtown at River Point in nutrition and exercise physiology with a master's program where they look at all the changes that are occurring during exercise. And so there's a lot of cool stuff coming out about weight gain and weight loss and exercise, looking at it from a physiological standpoint. All right, so the other thing I'd like to do is quickly kind of review the order in which things around us exist. All right. So we can divide things on Earth into kind of two large groups, matter and energy. And when we're doing matter, then when I went to school, the lowest level of matter was an atom with its subatomic particles. And now we have neutrinos and stuff. It's like, wow, what are these things? Yeah. So science has to change all this. So I kind of left it kind of more generic. But anyway, So what we do know in terms of looking at the things we interact with, the chair you're sitting on, the table you're writing on, and your body, is it's made up of atoms. Yeah. Right? And then atoms are constructed of subatomic particles. So the three subatomic particles are protons, neutrons, and electrons. So the first premise of an atom is that it has this thing at the center. So what do we call the thing at the center of an atom? Nucleus. Cool. And what do we call the thing at the center of a cell? Right? So if we have a nucleus, what of those three subatomic particles would be found in it? Protons, protons, and neutrons. Okay. So what we would see is that we would have, at the minimum, protons. That would be true of hydrogen. And any atom above hydrogen has a combination of protons and neutrons. Okay. So the periodic table is really cool. The guy that figured this out, he put so much information in that thing, if you know how to read it, it's just amazing. So anyway, I don't expect that. So anything above, so the next one would be helium and above, all have protons and neutrons. So then where are electrons found? In an orbit around here. Yeah. So there's this magic thing out here called an orbit, or an energy shell. That's where the electrons found. And further away from the nucleus, the more wide that electron field is, right? So you never think about this, but your electrons are bouncing off their neighbors, right? And those are energy fields. So what keeps an atom together? Charge. So we have three things up here: electrons, protons, and neutrons. Who's charged and who's not? So let's do the easy ones. What name tells you it isn't charged? Neutrons are neutral. Cool. All right. So pro, positive. Say pro electron is negative. And it's the difference in charge between the proton and the electron that keeps the atom together. There's a static charge. Cool. All right. So, even though you can look at a periodic table and you can be just amazed at all this stuff up there, we're all made mostly of the top two rows. So that makes biology easy because we're 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, 2% calcium, 1% phosphorus, and then it just goes down from there. We're more than that, but those are our major atoms that we are comprised of. Okay. So if two or more atoms interact together, we call it a molecule. So the way atoms interact is they form bonds. Yeah. So we form bonds. So to our understanding right now, there are two types of bonds: covalent bonds and ionic bonds. So covalent bonds are the sharing of electrons. And that's the way most of your large molecules that make you up are put together, is with covalent bonds. So what we're going to do is we're going to look at the type of molecules that make you up in a minute, But if we were looking at covalent bonds, then the covalent bonds would make up lipids that make you up, would make up sugars that make you up, would make up proteins that make you up, would make up DNA and RNA that make you up. So almost all the major biological molecules that actually construct your cells are all put together with covalent bonds. Now, the coolest molecule on Earth is actually water. Because without water, none of us would be. And it's actually because of the way water is constructed that everything on Earth works the way it does. And what happens with water is that we would write it as H2O, and that tells us it's 2 hydrogen and 1 oxygen. And we know that because of the way the electrons are found in oxygen, that the molecule is designed like this, where the hydrogens are on one side instead of across the molecule. And because the hydrogens are on one side, and because oxygen is an enormous molecule, number 8 up there compared to hydrogen, so the atomic weight of oxygen is 16 if we round it up. The atomic weight of hydrogen is 1. So hydrogen has 1 electron, 1 proton. Oxygen has 8 electrons, 8 protons. So because this guy has 8 protons, it takes the hydrogens from, it takes the electrons from hydrogen, so they spend more time over here. So it gives this molecule a negative field and this part of the molecule a positive field. So it's a polar molecule. And it's created by what we call polar covalent bonds. And it's the fact that water is a polar molecule that drives all the way up to the world. Amazing. The director's giving us science. Okay? Isn't that cool? Do you ever ponder that? You see it every day. You put ice in the glass and fill it with water, what's the ice do? Flows. Because water is a polar molecule. And you can't make it that dense as a solid. So water is one of the few molecules on Earth that is less dense as a solid. What about ionic bonds? What happens in ionic bonds? So one atom gives up what? Electrons. Yeah. So what we do is we exchange electrons, where inherently in covalent bonds we're sharing electrons. But if we have a polar covalent bond, we're not sharing equally, right? So what happens, and I used to do this, until I blew up a beaker in the class. But I decided it was a risk that I probably shouldn't take. But I used to take metal sodium and drop it in a beaker with water. And then what would happen is all the electrons from the sodium would be given off to water. And when those electrons left the atom, it releases an enormous amount of energy. Boom! I just didn't quite get the amount of sodium in water. So if I were to put sodium in a beaker with chlorine, what would happen? We would make, so if I did this, I'll write it like a chemistry grade. I will make sodium chloride. And what happened? Sodium, which one got the electron? Which one gave up the electron?
Sodium.
The periodic table tells you certain stuff. These guys have 1 electron or 2 electrons in their outer energy shell. These guys need 1 or need 2. So if you need 1, chlorine, and you're given the chance to react with nitrogen that would like to give up 1, because then all its energy fields are filled, then it's going to readily give it up. Yeah. So ionic bonding is easy because you just look at the 2 extremes of the periodic table and voila, that's the ones that ionically bond. So if we put this in water, then we end up with sodium ions, and we end up with chloride ions. Bingo. Your body would not be able to do most of what it does if it weren't for ions. So sodium is an ion you need. If you don't have enough sodium, you can go into a coma and die. If you have excessive amounts of sodium, you can go into a coma and die. So ions become very, very important. Okay? So when we look at the biologically important molecules that I listed up here that are covalently bonded, proteins are critically important. And the way our body works is most of these critical molecules that are covalently bonded, we have to get from somewhere. So how do we get them? Through eating. We let a plant make them. We let a cow make them. And then we use them. Right? But plants and cows have some unique proteins. So do we just want to incorporate a protein in our body from the other critter? No. So what's our digestive system? Breaks it down. So what we do is we ingest pre-made large organic molecules, and our digestive system converts them to the building blocks that we need to make our own. So what do we need to make proteins? We need amino acids. Those are the building blocks. So we ingest pre-made proteins, not because we're going to use those proteins like that, but because we want to break them down to retrieve amino acids, and then ship those amino acids around your body to make new things. All right. So the same thing is true. Carbohydrates are sugars. So there are 2 really large sugars that we ingest. So if it's plant material, it's starch. And if it's animal material, it's glycogen. And those are 2 really large sugar molecules. But again, our body doesn't want to do anything with starch. So what do we want to do? We want to take the starch and we want to break it down to its simplest form. So what complex carbohydrates are made up of is simple sugars. So if we're dealing with starch as a complex carbohydrate, the simple sugar would be glucose. And that's what we're interested in, is the glucose. So we have this cool digestive system that does nothing but break down large organic molecules to give us the material we need to make new molecules for ourselves. Nucleic acids. Now this is the cool. So everything you eat has DNA. That DNA codes for some cool stuff. Broccoli DNA knows how to make flowers. Now, would you want to incorporate broccoli DNA into your genome? Because then you could flower. It's green because it has a DNA that tells you how to make chlorophyll. That might be cool. We could just stop eating if we did that. Or you just lay out in the sun, turn your eating. We make energy for ourselves. Or what about pig DNA? Chicken DNA? Salmon DNA? You could have fins. have to do with DNA, obviously. So we take all the nucleic acids we ingest, and we convert them to nucleotides. And then we can remake our own DNA. Very fundamentally important. Right? Then the last one would be lipids. Fats. And so what we do with fats is we actually break them down into fatty acids and glycerol. So that's the one that probably is kind of the interesting thing to look at. So let's deal with fat. So glycerol is a 3-carbon compound. So that's the glycerol molecule there. And what we attach to it are these long carbon compounds. These long carbon compounds are called fatty acids. And so potentially, because we have a 3-carbon sugar, then we can have a fat that has 3 fatty acids. So if you do that, then we just use a prefix that tells us that. So triglycerides are all fats that would have 3 fatty acids on them. So we tell you that by using tri as the prefix to glyceride. So a diglyceride would only have 2 fatty acids on it, and a monoglyceride would only have 1 fatty acid on it. Okay? So that's a cool thing. The other thing about fats, which is really cool, I don't know if you've ever pondered this. See, I went into science because there's all this stuff around me. Why? So you go to the grocery store, and your grandmother sends you, and she says, I need some Crisco. So you go to the grocery store, and then there's stuff in a jar that's solid, semi-solid, and there's just stuff in a jar that's a liquid. And then you're like, well, what was I supposed to get? These all say Crisco. And what's the difference? Why is it solid in this container, and why is it liquid in this jar? Do you ever wonder that? You guys have missed out on a lot of cool stuff. All right, it's all based upon the bonds between the carbon. So, at room temperature, if a molecule has all single bonds, all the fatty acids have single bonds, then it's going to be butter, lard, Crisco. It's going to be a semi-solid at room temperature. And we would say this is a saturated fat because it has all single bonds in it. Harder for your body to digest.
Isn't it saturated with hydrogen molecules?
Yeah. So if we drew everything, so I'll do it with just one of the 2 carbons because then I can demonstrate it for you. So yeah, saturated fat, each carbon has 2 hydrogens. Yeah. Okay. So if it's a liquid, it has double bonds. But if you look at where carbon is, it's on the 14th column there, and it's 4 over from the 18th column. So carbon can interact with 4 other electrons. So when you make a double bond, you get rid of 2 of the hydrogens. So it's not hydrogenated. And double bonds are weak places where we can digest them better. But it also changes whether it's a solid or a liquid at room temperature. Isn't that amazing? Just a few little bond differences. So why do we have biological molecules? Because we construct cells out of them. Membranes of cells are mostly lipids. The structural components that define the shape of a cell are mostly proteins. What drives the activity of a cell is DNA. So we have these 4 biologically important molecules because that's what our cells are constructed of. Right? So the cell is generally viewed as the smallest functional and structural unit of the human body. There's a debate now. Viruses have always been considered to be non-living entities, because typically they can't do anything by themselves. They don't have both DNA and RNA, but only DNA or RNA. But now there's some new stuff that might make us change that. So in the future as well. But for right now, cells are the smallest living entity because they can do things by themselves. So if we take a cell and we cut it together, then we form tissues. And so what your organs are constructed of are tissues, which are organized arrangement of cells. So tomorrow in lab, we're actually going to look at one of the most common tissues in your body, which are epithelial tissues. And they are highly organized arrangements of cells into very predictable patterns. And so what we're going to do is we're going to classify them based upon the cell shape and how the cells are put together. Right? And then next week we're going to do connective tissue, which is another very broadly distributed tissue in your body. And then we're going to do the integumentary system, or your skin in this unit, because it's only comprised of those two types of tissues, connective tissue and epithelial tissue. Right? And then when we do bones, we're actually going to do bone tissue, we do muscles, we do muscle tissue, we do nerves, we do nervous tissue. Okay? So organs are composed of two or more tissues that function together. Organ systems require several organs to interact with one another to create a common function. So one of the things I wanted you to do in lab yesterday was to look at the organ systems of the human body and begin to understand a basic premise. So if I say endocrine, it's because they all make hormones. All right? So what we do is we look at how organ systems work, what their unique functions are, and then we kind of put them together. So in this class, this quarter, we're going to talk about the integumentary system, skeletal system, muscular system, and nervous system. In 242, because you guys are going to get better at being A&P students, because your foundation is going to be built this quarter, then we could talk about more systems. And so in the next unit, we're going to do cardiovascular, lymphatic, respiratory, digestive, urinary, and reproductive. And so next quarter, we're going to kind of pick up the pace a little bit. But most students actually think that quarter is easier than the first one, because the first quarter you're building your foundation. All right. So there's been an amazing debate throughout human history as to the idea of life and the difference between a rock and a living entity. And so what are the properties that living entities have that rocks don't? Okay. So when we kind of look at that, we have a high level of organization. Rocks have a high level of organization. You don't believe that before. It's amazing carbon configuration into crystals. But rocks are not composed of cells. So that's unique to living entities that are composed of cells. And then what we can do if we look at all the living entities on Earth right now is we can divide them into two types of cells, prokaryotic cells and eukaryotic cells. Who remembers the difference? Or better yet, what kind of cells do you have? Eukaryotic. Yeah. Unless you got a virus in your nose. Or a bacteria. So eukaryotic cells have what? A nucleus. So our lower digestive system, our large intestine, creates an environment for a bacteria to grow. E. coli. And E. coli is a prokaryotic cell. So we actually use prokaryotic cells. Actually, a recent published paper is probably going to change diets quite a bit. There's a guy who has looked at the number of bacteria that's in your gut. You can have up to 1,000 different species of bacteria living in your large intestine, even though E. coli is the most common. And what he's found is that depending upon the flora that you have, you either put on weight easy or don't put on weight easy, based upon the relative percentage of bacteria of different species that are in your gut.
Is more
And you
matter?
can influence it by the food you eat.
Or more, is it more?
No, it's actually not more species, but some particular species. If you have more of these particular species, then you don't put on weight. And it's influenced by what you eat. So that's taking what you eat and living in a very different realm than you've ever looked at. People thought he was kook when he first did his work. He's got some really good evidence. He's now done clinical trials with patients. Yeah, so it's really cool. So the other thing that cells do is they do this biochemistry stuff, these interactions, chemical reactions within themselves. So we use the word metabolism to describe the various chemical reactions going on in the body. Okay? So metabolism is the sum total of all biochemical processes at the cellular level, tissue level, organ system level. When's the last time you saw a rock walking down the street? You didn't see it falling down a hill, but not walking down the street. So one of the things we think is unique to life is this kind of movement, responsiveness. Right? So, well, when's the last time you saw a tree walking down the street? So since a tree doesn't move externally, can I assume a tree is a non-living unit? No, because they're moving stuff internally. So we can think about movement at the organ level, at the species level, but certainly cellular and intracellular movement becomes really critical to that thought process. The whole art of medicine is trying to keep people in homeostasis. So the simplest way to look at health is if you're doing fine, you don't need any intervention from drugs or anything, that's because you're in homeostasis. When you go to the doctor, how do we determine whether you're in homeostasis? We take a blood pressure, we take a body temperature, we take a pulse, and we use those values to determine whether somebody is in homeostasis. Somebody has chronic high blood pressure, they're no longer in homeostasis. And we have to use drugs to bring them back into homeostasis. So the simplest way to look at medicine is it's the art of creating homeostasis for people, right? So it's the ability to maintain an equilibrium. Now, the problem with the word equilibrium is some people interpret equilibrium as a static thing that never changes. That's not true. So it's a dynamic equilibrium. As we just talked about, if we did a pulse on a newborn baby and a 30-year-old and 80-year-old, the pulse would not be the same. So can we assume that the baby or the elderly person is out of homeostasis? Well, maybe the elderly person. Probably not the baby. But that's because it's a dynamic equilibrium that changes. Body size drives pulse and rate. The smaller the organism, the faster the pulse rate. The smallest hummingbird heart beats 1,000 times per minute. How can you count that? Think about it. Think you little bit. Yeah. So it's really cool. You can do statistical correlation through mass index and pulse rate. And you map out the person. The smaller you are, the faster you are. Right. So homeostasis is this cool thing we're going to talk about. And then the other thing is that rock sits there and doesn't change over years. Maybe it breaks up because of ice and stuff. But we differentiate. You know, and that is the coolest process. Every one of us started our existence as a single cell. Then we became two cells,
4 cells, 8 cells, 16 cells, 32 cells, 64 cells. And at one point, we were a ball of cells that we could count 128 cells in, and every cell was identical. You could not distinguish between any cell. And then this mystery happens where the cells take on different shapes and functions. And so we go from a cell that is identical, and so I'm going to use a couple words here, and I'm not going to test you on them, but we're going to use them later to learn how they're used to explain some things in the way we describe cells, okay? So we started, those cells where we were all identical are called blastomeres. So long story short, these are the embryonic stem cells that all the ranges went about, because all those cells are identical. No cell has done any differentiation. But what we go then is we go from blastomeres to 3 basic tissues that we need to make our body. So we form an ectoderm, and we form an endoderm first. And essentially, this is going to form our skin and our nervous system. And this is going to form the lining of most of our body, ducts, surface, internal linings. So the biggest one would be the GI system, the entire lining from your mouth to your anus. Okay. And then we form mesoderm. So the process of going from a cell that looks identical to differentiated cells is this process of differentiation. But we need to do that before we can make any of our organs. And once we can do that, we can make our organs. And then we grew, because we started out really small. Mom was really happy that we were small instead of this size, trying to come out really tiny. And then we grew. So that differentiation and growth. And then reproduction. So ideally, we think of reproduction as making new little babies. But you make 2 million red blood cells per second, making new cells. If you're male and 19, you're probably making 40 million sperm per second. So there's a bunch of stuff going on where we make new tissues, we repair tissues that are aging, and we replace tissues. And the amazing thing is that we have this amazing capacity to really make a bunch of new tissues, and then we have certain organs where we can't make new cells. So when I took anatomy, they didn't think the liver repaired itself. But now we know that we can take a donor, take half of their liver, stick it in someone else, and in a year or two, both individuals will have an normal sized liver. We didn't think that when I was in school. I believe it or not, we were told that the liver didn't repair itself. Your heart does not repair itself. So when you have heart attacks, you live with the permanent damage to your heart. And if it's significant enough, you die. Or you have to get someone else's heart through heart transplant. What if we could figure out how to make cardiac cells undergo mitosis and repair damaged tissue? We would never have to do transplants again. And you could repair your own heart. Limited success with stem cells in animals with heart repair at this point. It's work being done at Johns Hopkins University. So that's a cool process we're going to talk about. Cancer is cell reproduction non-destructive. So the thing about science that always cracks me up is the idea of evolution, and how strongly some people feel in those perspectives. And to me, it's just kind of a logical thought process. So to begin with, the first thing I said was, science deals with things that you can observe and create an experiment to test. So where humans came from is not tested. It's experimentation. So I never worried about it. Right? So, because some people are adamant, then they think that, well, because their view of evolution is how where humans came from, then it doesn't exist. But you're missing the point. Evolution does exist, and it's testable, and you can do experiments on it, and you can demonstrate it. But you can't do it with humans. You can do it with bacteria and other things. And we've been doing a wonderful experiment in the United States with antibiotics and bacteria for almost 100 years. And we have the clear evidence of evolution among us. We have antibiotic-resistant tuberculosis. We have antibiotic-resistant gonorrhea. We have antibiotic-resistant syphilis. And we have MRSA, killing people in our hospitals and care facilities every day of the year. Actually, if you look at the data and you assume that the U.S. healthcare system is the best in the world, then you haven't looked at the data. We're 45th in mortality. We have more people dying in hospitals and care facilities unneededly than most of Europe. Okay. So, MRSA is a bacteria that's the most common bacteria on your skin. And what we've done with antibiotics is make it more and more resistant to antibiotics. So it's on your skin, it's great. If it's in your bloodstream, you're dead. It's just, it doesn't belong inside, it belongs outside. So what we have is we have MRSA, which is methicillin, which is all of the penicillin-based antibiotics, resistant Staphylococcus aureus, which means that no penicillin-based antibiotic does it. And so what happens if you're in a hospital and the patient has MRSA? They're in an isolation room. As a clinician, what do you have to do when you go in to see them? Gown up, mask up, glove up. Do you then walk down the hall the next room with that gown and mask and gloves?
All things have to come off before you even exit the area. You have to send infection.
What if the patient's family wants to come visit? Yeah. So we're trying to deal with it because it's killing people. Unneededly. In hospitals all across the United States. Thousands of people. Right. So the good news, it used to be only in hospitals. The bad news is it's no longer now only in hospitals. So we had what was called HA-MRSA, which was healthcare associated MRSA. And now we have CA-MRSA, which is community associated MRSA. Do you ever wonder why those funny towels showed up at all the grocery stores where you're supposed to wipe your hands and then wipe things? You ever wonder? Oh, they just got clean. That's good. Because we're trying to limit MRSA. So I used to do this experiment to try to convince kids that we can talk about macroevolution, and I don't really care about it. We can talk about microevolution, changes in gene frequency and population, and I can demonstrate it to you. I used to do this clever experiment where I would take with a student, and I would take an auger plate, I would pour it at an angle, and then this auger had antibiotic in it. Then I would pour auger over it that didn't have antibiotic in it. Then I would grow bacteria on the top of it. Well, the reason is because the bacteria over here are in contact with the antibiotics. So what then I could do is I could eventually get some bacteria that grow right at this edge. Bacteria grow like crazy over here, but not as much over there. Then what I would do is I would take another petri dish after we'd grown these, then I would reverse it where I put agar without antibiotics down here, agar with antibiotics here. That created a concentration gradient where you had low levels of antibiotics here, you had high levels of antibiotics here. I would take this resistant bacteria and put it over here. And eventually by the end of a quarter, we could take this same idea and start growing over here with the highest level of antibiotics and they'd be fine. Didn't bother me anymore. Evolution in action. Change in gene frequency. Yeah. So the take-home message for me is I don't really care about macroevolution. But if we as a society decide that evolution doesn't exist, then we're in trouble. Because it does exist and it kills. All right. So homeostasis. That's what keeps us going. And we use all these things in the hospital, and we can go to the doctor, blood pressure, temperatures, to figure out whether you're in homeostasis. Well, your body tries to maintain homeostasis throughout its life. And there are two systems that are fundamental to that. Your nervous system and your endocrine system. Okay? They are the ones that are designed to try to maintain homeostasis. And then, as I said, homeostasis is constantly being challenged. So, if I were going to take your pulse rate, and I decided I was going to do it 3 different times of the day. So, the first pulse I was going to take was when you were in bed before your feet ever hit the floor. The other pulse I was taking would be when you were sitting in a chair watching TV, reading, or something. And the third pulse I took on you would be after I asked you to climb 5 flights of stairs. What would be your lowest pulse? Laying in bed. What would be your highest pulse? After you climb 5. So if you're using pulse as an idea of homeostasis, you have to understand that pulse is dynamic. It changes. Right? So you take, this is beautiful. I take my mom to all these doctors all the time. And it's so funny, because you'll take her, and then I'll have her walk back. And for you and I, walking from the waiting room to the exam room is nothing, but to an 80-year-old, it's something. So they put her in there, and then the MA takes her pulse right away. And then we wait for the doctor, wait for the doctor, wait for the doctor. And then a doctor takes her pulse. And take a guess, they're never the same. She will exert enough energy to get back to her pulse rate. All right. So basically, the point of that exercise was that there are always these disruptions to homeostasis. In most instances, they're mild and temporary, or body recovers from. So the key to healthcare is when people's own bodies can't recover from homeostasis, then it leads to death. And we try to then intervene with fill out the homeostasis by using drugs and other techniques. Amount of time. So what we're going to do is we're going to finish this real quick, looking at feedback mechanisms to maintain